When machine-learned climate models are pushed beyond scenarios they were trained on, they degrade catastrophically. Oceans boil while continents flash freeze, defying basic thermodynamic laws. These perfect model emulators are designed to replicate the output of traditional physics-based models at a fraction of the computational cost. When running the historical scenarios they were trained on, they are remarkably accurate and up to 100 times faster. The breakdown occurs when two critical climate drivers, sea surface temperature, or SST, and carbon dioxide concentrations, are decoupled. If a model encounters a combination of ocean heat and greenhouse gas forcing it hasn't seen before, the predictions become unphysical. A standard way to test this boundary is the AMIP plus 4 Kelvin experiment. In this simulation, global sea surface temperatures are uniformly raised by 4 degrees, while CO2 is held completely constant at historical levels. This map displays the 2-meter temperature response in the previous generation ACE2 SHELD model. Despite a uniformly warmed ocean, the emulator erroneously predicts significant temperature drops over land masses and sea ice. The darker the blue, the more severe the unphysical cooling. The root cause lies in the training dataset. In historical observations, sea surface temperatures and CO2 concentrations rise together. They are highly correlated. Neural network architectures are highly efficient pattern matchers. Because these variables always moved in tandem, the network used their correlation as a mathematical shortcut, rather than calculating the underlying physics driving each variable. Entangled training data prevents the architecture from learning the isolated, independent effects of surface warming versus greenhouse gas forcing. When one changes without the other in a test scenario, the mathematical shortcut fails. This failure extends to temporal dynamics, which becomes visible when the atmosphere is coupled to an interactive slab ocean. A classic diagnostic for this is the abrupt 4 times CO2 experiment, where carbon dioxide is instantly quadrupled. Physically, the atmosphere and ocean take time to adjust to such a massive shock. The expected response is a gradual, transient equilibration spanning decades as the system absorbs the new radiative forcing. This chart tracks global mean stratospheric temperature. The black line represents the physics-based target model, SHIELD. The blue line is the previous emulator, ACE2 SOM. Instead of the gradual cooling seen in the physics-based target, the emulator's stratospheric temperature drops nearly vertically on day 1. The model bypasses the transient physics entirely. It jumps straight to a quadrupled CO2 equilibrium state within days, ignoring the thermal inertia of the simulated Earth system. This immediate jump requires energy to vanish from the system instantaneously, violently violating the laws of global energy conservation. When forced outside the bounds of correlated training data, the machine learning architecture fails across both spatial patterns and temporal timescales. To fix this, the machine learning model must be forced to learn the distinct physical pathways of sea surface temperature and CO2. Plotting sea surface temperature on the x-axis and CO2 concentration on the y-axis, historical data forms a tight diagonal line. This leaves vast, empty quadrants. The model has zero data to learn how climate behaves in these off-diagonal regions. The solution is a newly engineered set of reference simulations called Ramped SST Random CO2. These runs are specifically designed to populate this void. In these simulations, sea surface temperature is prescribed to increase at a steady rate of 1 Kelvin per year. Simultaneously, CO2 concentration is randomized every 30 days, scattering wildly to ensure combinations of SST and CO2 are completely decoupled. This graph displays the time series of this engineered forcing. Panel A shows CO2 concentration jumping logarithmically over a 5-year period. While CO2 forcing is erratic, the resulting temperature responses in the troposphere and stratosphere exhibit their own distinct, complex reactions. Generating this artificial, decorrelated data manifold removes the mathematical shortcuts. To minimize error, the neural network is forced to calculate the independent pathways for surface fluxes and greenhouse gases. We measure the newly trained model, ACE2S SHIELD Plus, by returning to the +4 Kelvin test. As a reminder, this error map from the previous model shows severe, unphysical cooling over land and sea ice. Panel G shows the new ACE2S HIELD Plus model. The spurious cooling is entirely eradicated, resulting in a near-white map indicating minimal bias. The global root mean square error drops from 3.61 Kelvin in the old model down to just 0.22 Kelvin. The model achieves this high accuracy despite never seeing this exact combination of warm sea surface temperatures and steady CO2 during its training phase. By comprehensively filling the phase-phase void, the model's predictions align with actual macroscopic physical laws rather than spurious data correlations. We also test the new model's temporal response using the abrupt quadrupled CO2 coupled experiment. These charts show the evolution of upward and downward radiative fluxes. The energy-violating jumps are gone. The orange line representing the new model closely tracks the gradual transient response of the dark gray baseline. A far more demanding test of implicit physics is examining how short-wave radiation responds, a process heavily mediated by clouds. This map shows the top of atmosphere upward short-wave flux. The target baseline is on top, and the new model is below. The model accurately emulates the reduction of marine stratocumulus clouds, visible as distinct blue zones off the coasts of the Americas and Africa. Notably, the new model captures this complex cloud pattern without having an explicit cloud variable anywhere in its state vector. Highly complex coupled physical dynamics implicitly emerge from the network naturally, provided the underlying training data is fully decorrelated. While this approach resolves the entanglement problem, evaluating the boundary conditions and limitations of this framework is necessary. First, this system operates entirely within a perfect model emulation framework. Because it is trained specifically to emulate the physics-based SHIELD model, it inherently inherits all of SHIELD's biases. It does not map perfectly to raw observational reality. Second, this configuration relies on prescribed, annually repeating sea ice data. Prescribing the sea ice suppresses vital long-term albedo climate feedbacks that would normally occur under increasing CO2 concentrations. Third, while the model remains stable for a millennium in most scenarios, one specific 1,000-year run experienced an unphysical stratospheric regime shift at year 506. Finally, these statistical improvements are currently validated across only 2 random parameter seeds. Structural limitations remain, but engineering independent training variables provides the definitive blueprint for teaching machine learning emulators how to handle other heterogeneous forcings, like atmospheric aerosols, in the future.